Good afternoon, everyone, and welcome back to isifundi training, and welcome to the final discussion in our six-part Bite-Sized Corrosion series, where we've been looking at vandalism and theft within cathodic protection. My name is Vanessa Seeley-Fisher, and it is, as always, a great pleasure to host today's discussion. Now, in this series of isifundi training's Bite-Sized Corrosion, we've been digging into a collective experience about the vandalism and theft challenges which face the cathodic protection space. We've been exploring some improved solutions. We've been trying to understand some of the nuances of the vandalism problem that we experience. And again today, I'm delighted to welcome a very familiar face back to the mic in Neil Webb. Neil is the Technical Director at Isiniti, with many more than 40 years of experience in designing cathodic protection systems. And as always, Neil, it's wonderful that you could join us. Thank you. Neil, last time we were discussing some technical solutions that we can consider when we are exploring the issues of vandalism within the cathodic protection sector. And while we know that the vandalism challenge in and of itself is really outside of the bounds of the engineers on the project, there are some things that we can do from a technical perspective that can change the situation, hopefully for the better. And we mentioned yesterday that the modern high resistance coatings, that with these, we now actually have the luxury of considering locating an impressed current system in perhaps a less than optimal location, but which is more secure, or we started to explore the use of sacrificial anode cathodic protection. So I thought to start off today's conversation, I'd like to just explore why choose which one. I know when I started in the industry, sacrificial anode cathodic protection was always considered to be significantly more expensive than impressed current, particularly on longer pipelines. Would you say that still holds truth?
I don't think so, Vanessa. Just recently on one of the big projects, we had the opportunity to actually do an alternative design in a tender document. So we had the main inquiry based on the use of impressed current, and then an alternative tender was allowed based on sacrificial anodes. And that wasn't a contractor design, it was an engineer's design. So it wasn't coming from somebody who had an axe to grind or a product to sell. And so in that particular situation, it was a typical pipeline in that it was relatively large diameter. I think it was 900 diameter, 40 kilometers long, a lot of AC interference mitigation required. And the alternative design was then based on the use of sacrificial anodes and a high electrical resistance coating, as you've said.
Right.
And in fact, the sacrificial anode design came in less than the impressed current design, believe it or not.
Gosh, that's quite scary to think about because it almost doesn't make sense. But I guess the cost of the impressed current systems are dramatically increasing because we're having to build all these extra protective mechanisms around them.
Well, not only that, but in this particular situation, the AC interference played a significant role. And because as we are seeing, pipelines are having to follow the same servitudes as power lines, the AC interference aspect is increasing. The AC interference on the high insulation value coatings is greater. So with an impressed current system, we then had the AC mitigation as well, together with all the DC decouplers associated with that, because you have to have those if you've got an impressed current system. So with the sacrificial anode design, it was quite outside the box because we integrated the cathodic protection and the AC mitigation design in a single system, a single sacrificial anode-based system. So we had a combination of zinc ribbon electrodes for AC mitigation and zinc anodes for cathodic protection. And they were spaced out along the line according to the interference aspect for the AC side and the number and mass of anodes required for CP. And the two were put in together. Well, they actually never did get put in because the pipeline was never constructed. But the tendered price for the two systems showed that the sacrificial anode system was in fact viable and in fact less expensive than the impressed current system. So it was a lower capital cost. And the the system was then optimized so that the cathodic protection aspect of the installation was grouped into relatively few anode installations. So going back many decades, in fact, where we used to put sacrificial anodes in the ground at 50 meter centers, and the number of anodes was decided by the diameter of the pipe. So if you had to replace that, you have to go and dig it up every 50 meters.
Which is a lot.
Yeah. And the advantage of these high resistance coatings is that the sacrificial anodes can be located at significantly larger intervals. So in this particular case, we used valve chambers as a ready-made connection point, and we had anode installations at 500 meter intervals. Right. So in 30 years' time, you go back and you replace a block of anodes every 500 meters. It's not such a big deal. Like I said, that on paper, they came out less expensive. Subsequent to that inquiry, we have in fact actually had a couple of pipelines, not quite so large, where we have implemented exactly that. The combined AC mitigation and cathodic protection without the use of decouplers, and it has been very successful. In fact, we presented that as a case study at one of the CIACOR conferences recently, showing the success of the installation.
That's really interesting, Neil. I think you may have already answered the question, but if you're using zinc as the CP and zinc as your AC mitigation, you're no longer requiring to decouple. And part of me is going, correct. How does the current know which zinc piece it's supposed to go to?
It doesn't. It will follow the path of least resistance, like electricity always does. But the point about that is that what we did was that the zinc anodes that were installed for cathodic protection were specifically located in low resistivity environments, firstly, and they were surrounded with the gypsum bentonite backfill in order to maintain them active. So that does provide a preferential corrosion situation compared to ribbon just laid in the trench, which is run of trench backfill.
And Neil, in the instances where this kind of design has been implemented, has there been a, can I say, willingness on the side of the client to have less perhaps monitoring infrastructure or less visible monitoring infrastructure? Have you been involved with any designs where you've been combining essentially some of this buried or hidden infrastructure as well as the use of anodes? Or is that a much more recent development and hasn't yet been tested?
Hasn't really been tested. The systems that have been installed are still connected at typically 500 meter centers. And those connection points then act as monitoring points, which allow you to monitor. The installations were associated with valve chambers. The civil engineers have upgraded their valve chambers significantly because they've had their share of problems. You know, people go in and steal valves. They steal chamber covers. They steal anything that can be recycled and sold.
Yeah.
So the chambers themselves have been upgraded as well. And that has enabled us to still monitor the situations. But the other aspect of this whole system is that as long as you've got access to the pipe at some point, you can monitor using, for example, close interval surveying. You don't have to have the test posts every couple of 100 meters or whatever.
Indeed. Now, Neil, before we leave this, another thought that has crossed my mind. If we're trying to do these zinc connections so they won't be vandalized, and I am aware of some that are being done not at valve chambers, so the monitoring may be done at valve chambers, but the zinc connections are happening somewhere else along the line to preclude the vandalism. What impact is that having on these close interval surveys like your DCBG, like your SIP survey? Can we still see what's going on, or have we now created another problem that we need to scratch our heads about?
Well, we certainly do need to scratch our heads in terms of surveys, because whoever is doing the survey needs to be aware of what is being installed. Now, certain installations, they have endeavored to make the anode connections such that they can be disconnected by putting links inside chambers, for example. in other installations, exactly as you've said, the anodes have been installed halfway between chambers deliberately. And then the chambers are purely used for monitoring. So even if everything gets vandalized, you've still got cathodic protection.
Yeah.
Yeah. And provided you know where these anodes are, you can see their effect in terms of surveying. So if you're doing close interval surveying from a potential point of view, presence of the anodes doesn't matter, because with sacrificial anodes, you don't really have an IR problem like you have with impressed current systems. In terms of DCVG, you've got a ready-made defect in the form of a sizable anode sitting in the ground at certain sections. Some of the problems, though, or the indications become a bit difficult. For example, if you've got long ribbon electrodes that are connected to the pipe permanently, they make DCVG surveying for coating integrity somewhat more challenging.
Well, I think, great things always come from adversity. So perhaps this is the start of someone developing some fancy technique that we've never thought of. Well, there's a thought for someone. Neil, we've spoken about the AC interference. And now the other big question that I have is DC stray currents. I recall when I started in the industry that the stray currents from the rail network were a perennial headache. And it was definitely drummed into me that the current chooses where it wants to go and how it's going to get there. And we have very little to say in the matter. And in my experience, the current routes are not usually via very secure locations, quite the contrary. So if we're looking at a system where sacrificial anodes would be preferred from a security perspective, how do we manage these stray currents? Because to the best of my knowledge, little pieces of zinc aren't going to fight against the rail.
No, you're absolutely right. The stray current situation on, let's call them legacy pipelines, is huge. We're talking about perhaps at the moment with some of the theft and vandalism we've seen on the rail infrastructure, we have seen a decrease in stray current activity in certain areas, but there's still a significant extent of DC electrified rail that is operational in South Africa, and it's gradually starting to come back into operation again. The problem's not going to go away. And with the low insulation value coatings, such as the old style bitumen fiberglass coatings, there's nothing we can do about that. We're going to have to stick with the heavy current, straight current mitigation systems where the Walgamachara pipeline, for example, it drains hundreds of amps continuously. Well, continuously, I mean, every time a train goes past. And those units are rated at 600 amps, the drainage units. In KwaZulu-Natal, on some of the Umgeni water pipelines, the drainage bonds, if you walked past the bond at night, you could see it glowing in the dark due to the current flow. That was a resistance bond to try and reduce the current, but it was still draining literally hundreds of amps. So that is certainly a challenge. But with any stray current situation, the stray current path itself is a series circuit. The current comes in one end of the pipeline and it goes out to the other end. Whatever comes in has to get out. But if you prevent it from coming in, you don't have a problem to get it out. And that's a bit of another off-the-wall thought. So if you increase the insulation value of the coating in the area of current pickup, now, when you look at an ACE course, it's a standard practice. You insulate the pipe in the area of pickup. Now, we kind of think, the pipes are coated anyway, so what more can we do? Well, we can increase the value of that insulation. Say, for example, by the use of the polyethylene-based coatings, where we have high voltage cables which are insulated with polyethylene that are running at thousands of volts,
and we
hundreds of thousands of volts, and we don't have a problem. So if you can insulate the pipeline in the area of pickup and prevent the current from getting into the pipeline, then you don't have to discharge it either. So what it does mean is that we're going to see very high negative potentials in the area of pickup. And we did, in fact, see that on the NMPP pipeline, for example. We were seeing potentials of negative 80 volts on the pipeline. And everybody goes, Yeah, we're going to get coating disbondment and everything else. But if you design your system to cope with those potentials, then the fact that you see those very high on potentials is not disastrous. Let's put it that way. And I know at one stage Transnet was in fact experimenting with special reference electrodes, coupons, and probes to actually try and eliminate the IR effect of stray currents in the negative direction. And they found that even though they were measuring tens of volts on the pipeline, when you looked at these IR-free electrodes, it showed that the pipeline potentials themselves were not anywhere near that. And so it really was an IR factor. We tend to think of IR as being only associated with the cathodic protection side of things in terms of making our stuff look more protected than it really is. But actually, in terms of stray current pickup, that IR factor is also there.
Real. That is very interesting. So it's not the unsolvable problem, but again, just looking at it with different glasses and being a little bit more creative.
Yeah, and it's something we have to do because we've had pressure from the pipeline design engineers that we work with, who in turn have had pressure from the clients saying, what can we do? Because we cannot afford to keep putting in this expensive cathodic protection system that gets vandalized at such short notice. Can we use plastic? Can we use fiberglass? What can we do? And certainly the judicious use of high value coatings and sacrificial anodes can go a long way in answering that challenge.
But I think also Nearly raised quite a valid point. I think there is a place, as much as it grieves me to say it, but there is a place to use the plastic pipes where cathodic protection installations have been vandalized, where perhaps pressures are lower, usually in water reticulation. And we're looking at that and not saying, steal at all costs, but actually it's become so costly that we can no longer say that. And we need to look at, and I also think credit where credit is due, that within the plastic pipe industry, there've been huge strides. The reliability has increased, the pressure ratings have increased. And as much as I don't really want to say don't use steel, I do think there is a place. And I think we need to acknowledge that. Quite a contentious issue. What about using discrete segments? So a mixed steel and plastic pipeline, particularly in high stray current areas. I know you are someone who sings loudly the drum of electrical continuity. How would you feel about discontinuity in terms of pipeline construction to try and break this electrical path?
Certainly discontinuous pipes, if I can call it that, segmented pipes, or jointed pipes, whichever you like to call them. If you do not have stray currents, then you can go that route. And it requires a lot less cathodic protection. You can use sacrificial anode systems in localized areas because you don't land up with these very long cells, which are set up by the stray currents. The problem with stray currents from the rail is that the electrical field is so vast that it actually extends way beyond the length of a pipe.
Right.
I mean, some of our stray current circuits that we have picked up extend over hundreds of kilometers. On some of the pipelines between Joburg and Durban, you can see the effect of traction movement in Gauteng down in Pietermaritzburg on the pipeline. So if you've got discontinuous pipes, if they were perfectly coated and remained perfectly isolated,
yes,
fine, yeah, but they're not, and so you'll find that the stray current then hops on and off these pipelines. And a very good illustration of that actually goes back to some old pipelines that were installed in the Northwest Province. Long before it was known as that, where they were Viking Johnson coupled pipes and coated, but not continuity bonded. And due to long cell action in the soil, we found that there was actually stray current corrosion inside the couplings. And so you landed up with, instead of the pipeline corroding at one particular point, corroded every 9 meters.
And that's the challenge with stray currents, is that getting rid of them safely is copper intensive on a jointed pipeline, because you do need to bond across each joint as well.
Unfortunately, you can't conduct stray current through fiber optics.
Yeah, one day someone's going to figure that out. And it won't be Neil. Neil, thank you. I think we probably need to draw this discussion to its conclusion at this stage. I think it is encouraging to know that there are practicable solutions that we can be using, not only to change the above ground and even the buried infrastructure, but also in terms of changing the design, revisiting the coating. I think there are avenues we can explore, and that the corrosion protection of a pipeline shouldn't be left to that last, oh, we forgot about it, but rather be incorporated right from the outset, so that the pipeline design engineers are also giving it the same considered opinion and approach to try and get a fairly holistic view to combat the challenge of vandalism and theft whilst retaining the benefits of cathodic protection.
There's one thing that I'd like to throw out there, and this is aimed at the pipeline engineers and the infrastructure owners. When we operate as independent consultants and designers, you're expected to come up with a working solution. You don't have the luxury of being able to experiment. And I would love to see some experimental or development work done on using AC interference to apply cathodic protection by means of directional, in other words, using diodes, for example, by using directional AC drainage using sacrificial anodes. So you land up with the AC in the pipeline as the driving force for the cathodic protection. And the result of that, you land up with impressed current cathodic protection with no wires.
That's certainly worth exploring, and perhaps something we need to get some think tanks happening around. Thank you, Neil, for the challenge. And I do hope that we have some interest in our audience who will take us up on that offer to have conversations to see where we can explore this a little bit further. So thank you for the challenge there. That does draw us to the end of this series on vandalism and cathodic protection. Just before we close, I'd like to remind you again that we've just launched our new CPD accredited online course on pipeline survey techniques, really looking at ways that we as isifundi training can help our engineering audience find CPD points that hopefully will be of value to them and also be affordable. You can see the link below, and we encourage you to explore the offering. This course is a comprehensive overview. It's got some questions. It meets X's requirements. And so there is a full CPD credit for the course. So we encourage you to use this resource for your professional development. The link is below. You'll also find it on our website and on our LinkedIn page.